All right, so here we're going to do 16.7 Stokes theorem, very similar to, or I guess I should say just a more generalized version of what we saw with Green's theorem a couple sections back. So here we go, we have a circulation vector at a point P in a plane and a three-dimensional fluid flow. So we're looking at how much is it, flowing around that point. We call that the curl. And we use the right-handed convention here, where it's going around counterclockwise according to the direction. So if you wrap your fingers around it, your thumb should point in the direction of that curl there. And that's because it's a cross product. So the vector is called the curl vector for the vector field F equals mi plus nj plus pk. And then you define this curl like that, which is ultimately, if you can write it out like this and memorize this, or you can just use your del operator that we know from Cartesian coordinates and just do the cross product with your vector that you're trying to find the curl of. Okay, and so you just do that cross product, and there you go. That's the curl of that vector function there that we're looking at. Here, finding the curl of one, pretty straightforward. You've got your vector field there, and you're just doing the cross product with the del operator. Obviously, this is for doing minors, so you cancel out this one, and that'll tell you the I component, which is this, the determinant of that minor right there of the matrix. So it's partial derivative with respect to y of x squared minus this way. So you crisscross and do the subtraction. Then you move on and you cross out the j in that column there. And so you're doing partial derivative with respect to x and partial with respect to y like that, crisscrossed, and subtracting them again. But this one you put a minus in front of. Then you go back to being a plus. So you alternate plus, minus, plus, minus, plus, minus. You do this. So now you look at the k component, and it's going to be this matrix right here you're doing the turnaround of. So crisscross again and subtract the crisscross like that. This one is a plus, so it's plus, minus, plus like that as you go through and do them. And then there you go, you end up with the k component right there, and you just take those derivatives, those partial derivatives, and it'll give you a vector here. That's the curl there. So you put in a specific point there, and you get the curl at that location. Here, we're looking at the curl over a surface, and so the idea here is, just like with Green's theorem, we can either go through and count up the curls in the whole area, or we can count up the curls just around the edges, because anything on the inside here is going to cancel out. You'll have it going this way and then opposite like that. And the only thing that's really going to be left is the curl around the boundary. And so essentially what we're saying here is this, that the curl around of the whole area is equal to just the curl around the line integral boundary of it. So this is our surface S, and this is the bounding curve C. And here it is again. So we can let S be a piecewise smooth oriented surface having a piecewise smooth boundary curve C, and then F is equal to mi plus nj plus pk, be a vector field whose components have continuous first partial derivatives on an open region containing S. Otherwise, we can't really take those derivatives. Then the circulation of F around C, so around our boundary C, in the direction counterclockwise with respect to the surface unit normal vector n, equals that integral with our cross product there. So that's essentially the idea there. Count up everything on the inside or just what's all around the outer edge. Okay, here is how you find this d sigma that's here, this d sigma. This was from a previous section, but I went ahead and copied it here. You have three different basic situations that you're going to come across where you have the parametrically defined surface. And you're going to do something like this. If you have a surface that's function of x, y, and z, and it equals to some constant, you're going to do this second one here. And then finally, if you have some sort of surface that's defined as a z equals a function of x and y, you're going to do this third one down there, and that'll give you what d sigma is. Now note that this unit vector p here is normal to the region, not the surface. So you're looking at the region down here, R, not the surface that you're looking at for. So this N is normal to the surface, and that P is normal to the region in there. like that. So p hat. Okay. Sorry, I kind of flipped away from that real fast, but you can go back and pause, I guess, if you want to look at it again. So anyway, that's how you can do this. If you want to see more information on this, look at page 1023 in your book. Here you can see the green theorem is our nice little special case of this, and then we can have these three-dimensional surfaces here rather than just the little two-dimensional thing that we were having in with green theorem. And so this is just the more generalized version of it compared to the green theorem. The green theorem is the special case, I guess we should say, of that. Here we can evaluate this. Sorry. Looking here, we want to go ahead and do this integration here and find this circulation vector. You can see it in the picture, the normal vector, normal to the surface, and then we have that k vector there that is coming up normal to the region in the xy plane there, which is just going to then be the k vector. So that's actually our p vector. So if we come over here, we can see that if we parameterize this up, we have this parameterization, we get dr, we can go through, take dr, do this as just a regular dot product, f dot r or f dot dr, go through, calculate it, and just do a normal integral essentially right here with the f dot dr. So a lot of times that one's simple. Or you see we get negative 18 pi, or you come down here, you do your cross product, right? You do your cross product and you get negative 2k. Your normal vector to the surface has to be pointed out radially away from the center to be normal to the sphere. So it's just the same amount in x, y, and z. So it's just xi plus y, j plus zk in the same direction there. And then you divide it by its own magnitude, which is the square root of x squared plus y squared plus z squared equals 3. That's what its magnitude is, because that's where our radius is at this point, is at 3 right there, right? It's equals 9, so that's 3 squared. So the radius is 3. So that's what its magnitude is there. So divided by its own magnitude, there's your normal vector. D sigma is then the gradient of our surface divided by, or the magnitude of our gradient of our surface divided by the magnitude of the gradient of our surface dotted with that p vector, which in this case is just k right there. You can see it is this k vector right there. And we can see on the next page I went through and actually did it. Here's the gradient I did up here. That's f, and then I took the gradient. And then down here, our gradient dotted with p is the gradient dotted with k, which just means we're just pulling out the k component, which is just that 2z up there. And so our d sigma becomes that gradient of f, magnitude gradient f over the magnitude of gradient of f dotted with p, the z component. And so this becomes 6 over 2z, which is just 3 over z, and then integrate over the area, so dA. So that's what we have. You come down here, the cross product of these, we replace this over with integrating around this circle. X squared plus y squared to less than or equal 9 is a circle. And so we're just really are going to ultimately find the area of that circle, because the z's are going to cancel out here and the 3's are going to cancel. And so we're just, basically it's just negative 2 times the area of that circle. So it's negative 2 times pi times 3 squared. And there's your negative 18 pi. And so both answers gave us that negative 18 pi, and they were the same. Over here is another example. I'm going to leave, I think I left for you. No, I did this one. So, or have it done in here. And so here we've got a cone, and we're going to go through and do, and try it on this one as well. So we have our region here, our bounding region C, and then our surface is that cone S right here, the orangey area there. And so we come over here, you can parameterize the cone. It's just a bunch of circles that get larger as you go up, as r cosine theta in the I direction plus r sine theta in the j direction plus r in the k direction. Then we're going from 0 to r equals 2 there, and 0 to 2 pi. So our normal vector here, since we have a parameterized cone, is going to be this right here, r sub r. So that's, in other words, r sub r on that previous page is dr vector dr, and r sub theta is dr vector over d theta. So this is the scalar r, this is the vector r. So that's this top one's r of t, the other one is like the variable r being in there. So, you know, we essentially have, so in other words, the top one is this r, and the bottom one is the scalar r inside it, and they're different there. And then, so r, the vector r1 is the function, and the little r is the variable inside it, that it is one of the independent variables there. And so you do those derivatives, and then you take those cross products, and you'll get this right there on the top. Then you take the magnitude of that cross product, which I did right over here. Right? I took the magnitude of that cross product, and you end up with r times the square root of 2. And so this just becomes 1 over square root of 2. The r's cancel out, and you're left with a normal vector there that's negative cosine theta in the I direction minus sine of theta in the j direction plus k. And so our d sigma becomes r times the square root of 2 dr d theta. And so that's what we end up with because it was parameterized and we use that. So del cross f is just equal to that. And then we can actually go through. Now we have the cross product here too, and you put those together, dot it with that normal vector we came up with, and you get this. And then that is what's going to plug in, and we're going to take the derivative of that. And so here we have the del cross f dotted with n. So that's this part right here. And then the d theta or d sigma is that part over there, becomes the r square root of 2 dr d theta. And you end up getting 4 pi. So if you were to go through and do this as f dot dr, you should get a 4 pi as well. Okay. Here you can see the surface and the vector field then going through it. In the first one's just the surface, the second one has the surface and then all the little vector fields, selected vectors in different locations. Here we can look at a curl as how much it would cause a paddle wheel to spin at a location. So the curl at a location would be, we put a paddle wheel there and we see how much it would make it spin in that location. If it won't make it spin, then the curl is 0. If it makes it spin a lot, then you're gonna have a larger curl. Here, I believe I left this one for you to try. This one, you have a fluid constant density rotating around the z-axis. And so you want to find the circulation around that. And so you should go through and try that one. Here's another one I was leaving for you to try. And I think you have some like this in your homework. We did some in class. So I think in the chapter 16 problems, there's one that I did like this. Notice this is the region down here. So again, your p vector is just going to be p equals k. And go through and do that just like we did on the one back there, a little bit back. And so you can go through and do that one. And again, I said there's an example of one very similar to this in the chapter 16 problems that we worked out, or mostly worked out. At least I put out all the steps you have to do it. Here is another one that I believe for you to try and figure out. And again, look at it, you know, projected down and everything into that there. So this is an elliptical paraboloid. So it looks a little wonky there, I guess, but what is c is x squared plus 4y squared. Yeah. All right. So go through and give that one a try as well. See how you can do on that one. Here, if you have different surfaces, you can actually just go around the edges and of course add them all up. So you can do it in individual sections for individual surfaces that are connected next to each other, which is, you know, kind of our typical idea. Here, if we have holes in our surface, that's not going to matter. You can still just go through and count up all of the curls around all of the boundaries and add them all up. So you'd have a curls around each of these inner boundaries and the outer boundary to go through and do like that. And so next one is a big one, other than just adding up the curls there around all the edges. This one tells us that the cross product of a gradient of a vector field, of a scalar field. So if we take the gradient one, is going to be 0, because if you think about it, del, which we're treating as a vector, is parallel to del f, because f is a scalar, right? Scalar. And so if we think about it abstractly, like this is del, then this has to be del times some scalar. It's either longer or shorter. It's just lengthened or shortened. And so that right there then tells us that if our curl of our gradient is 0, then we have, if our curl is 0, then we have so in other words, if it's del cross f, and it equals 0, then that's telling us that f, or implying that f is the gradient of a scalar field, which means it's going to be conservative. So conservative fields in Stokes' theorem, if we do the integral around this closed loop, it's going to be 0. So we're going to have no circulation in those conservative fields like that, essentially what we're saying right there. Okay, so it equals 0. Here, simply connected versus open connected here. What we can do is actually just split this up into 2 whenever it's crisscrossing like that. So you could do this side and then this side and add the results together. So you can just divide it into loops and apply Stokes' theorem there. Here is just a diagram summarizing the results that we got for conservative fields. And you can go through and look, and it tells you where we got those results and everything like that. So just a little summary of what implies what and everything. And that's it. So that takes the 16.8. So that's it. All right. So go ahead and if you need to go back and listen to any of this again or ask me any questions about any of it, just be sure to do that. Otherwise, that's it. And thanks for listening.